Okay, let's talk about this idea of differentiability, okay? And there's a theorem that says differentiability implies continuity. So if your function f of x is differentiable, again, that's just a fancy way of saying that you can take the derivative at some c, at some x value, some x equals c, then the function is also continuous at x equals c. So if you know that it's differentiable, and they'll give you questions like this. They'll say, they don't tell you the function, but they'll say f of x is differentiable at x equals 2. And then they'll give you these, which of the following statements are true kind of questions. And if it's differentiable, then if one of the statements says it's continuous at 2, then yes, that is true. However, continuity does not imply differentiability. You can be continuous, but not necessarily differentiable. Now, most functions, wherever they're continuous, they are differentiable, but there are some exceptions to that rule. So let's look at an absolute value function here for a second. For example, f of x equals the absolute value of x minus 2. Looking at the absolute value function, and based on what you know about the absolute value function, you should know that it's continuous everywhere. Okay, there are no jumps, there are no holes, there are no issues. It is continuous everywhere, but it is not differentiable everywhere. Okay, the absolute value function is not differentiable everywhere. And to prove that, we're going to write this as a piecewise function. So f of x is equal to the absolute, piecewise. Okay, so we change the sign for the left side, so when x is less than 2, and we keep everything the same for the right side when x is greater than or equal to 2. So now if I take the derivative of this function, okay, we know how to take the derivative using our power rule now. So you may want to rewrite this as negative x plus 2 so we can take the derivative of it easier. Okay, the derivative of negative x is negative 1. The derivative of 2 is 0. So for the left side of this function, its derivative is negative 1. For the right side of this function, the derivative of x minus 2 is positive 1. So this is kind of like our limits, okay? If the left-handed limit and the right-handed limit don't agree, then the limit doesn't exist. Well, the same thing happens with derivatives. If we have a scenario where we have a left-handed, so to speak, limit with this absolute value function, because the two sides of the function are different, if the left-handed derivative doesn't agree with the right-handed derivative, then f of x equals the absolute value of x minus 2 is continuous, okay, is continuous at x equals 2, but is not differentiable. And sometimes we abbreviate differentiable diffy. Okay, don't do that. I mean, you're probably not going to have to write that on the exam, but if you were, you need to write out the word differentiable. But just for time's sake and space, I'm going to write it. But is not differentiable at x equals 2. Now, anywhere else, we don't have a problem. At x equals 0, at x equals 7, at x equals negative 4, we're good. We're continuous and we're differentiable there, but at the vertex of that absolute value function, at the changing point of 2, it's continuous. The two sides of the function meet, but it's not differentiable. So here's our first condition for when functions are not differentiable. Functions are not differentiable at what we call sharp points. So the majority of the time that we're going to run into this is with absolute value functions, but there are some other functions where we run into some sharp points. So anywhere you see a sharp point, so in this case right here at x equals 2, it's not differentiable there. It's differentiable everywhere else, just not at that sharp point itself, okay? So moral of the story, we can take the derivative of the absolute value of x minus 2. We can take the derivative of that function. We don't know the rule for it yet, but I'm telling you, you can take the derivative of the absolute value of x minus 2 everywhere except for at 2, okay? All right, there's another scenario. We call it locally linear. Okay, we call it locally linear. So we're looking at the function x to the 1/3. Okay, that's also known as the cube root of x. If we graph that, we get a function that looks something like this. Whoops. Okay, here is our graph of x to the 1/3, or the cube root of x, however you want to look at it. Okay, here's our function. So let me show you something with this. Let's take the derivative of this function, f prime of x. Okay, applying the power rule, bring down the exponent, subtract 1 from the exponent. Let's simplify this. We've got 1/3, get rid of the negative exponent, so we move it to the bottom, x to the 2/3, and that is 1 over, let's go ahead and write it in radical form, the cube root of x squared. Now, let's see what happens. Let's just say what happens when we plug in 0, okay? So that's the derivative. We found the derivative. It exists, okay? That's not a problem. This function is continuous everywhere, okay? There are no jumps, there are no holes, there are no asymptotes. We're good. Continuous function. So let's plug in 0 into the derivative, okay? 1/3 times the cube root of 0 squared. Well, 0 squared is 0. The cube root of 0 is 0. So we've got 1/3 times 0. 1/0, that's undefined. Okay, we can't divide by 0. That's undefined. So the derivative does not exist at 0. We can take the derivative of the function. We did it there in purple. We found an expression for the derivative. But the derivative does not exist at 0. Okay, so f of x equals x to the 1/3 is continuous at x equals 0, but not differentiable at x equals 0. Again, everywhere else we're good. -5, 7, 10, 1. We're good anywhere else, but at 0, we're not differentiable. It's called locally linear because we have what we call a vertical tangent line there. Okay, remember, I think I mentioned in the last lecture when we were talking about some tangent lines, a horizontal line has a slope of 0 and a vertical line has undefined slope. So that's what's going on there. Remember, the derivative is the slope of the tangent line. So if the slope of the tangent line is undefined, that must mean that it's a vertical tangent line. That's an important idea to remember. If the slope of the tangent line, if the value of the derivative is undefined at a certain place, then there's a vertical tangent line at that place. So in this case, at 0, we have what we call a vertical tangent line. Now, you can't really see it on my graph right here, so let me show you. We're going to zoom in on it here. Let me type in, let's put it the way that it is on the paper, x to the 1/3. Or you could type in the cube root of x, okay? We're going to graph it, okay? This is kind of what my graph looks like. But if we zoom in, and I usually don't zoom, but just for the sake of time here, I'm going to zoom in on the graph, okay? If we get a little bit closer, see how it almost jumps? It looks like it jumps when the calculator is graphing it. Let me zoom in one more time. See that kind of jump from that one side to the other? It's because it gets so steep. Right there at 0, that's where that vertical tangent line occurs. So we've got two conditions where functions are not differentiable, okay? Obviously, if they're not continuous, they're not differentiable, okay? So if there's a hole, if there's a vertical asymptote, if there's a jump in the graph, then you're not continuous, so you can't be differentiable, okay? You have to be continuous to be able to take the derivative. That's condition number 1. But there are two cases where we are continuous, but we're not differentiable. That's at sharp points and at vertical tangent lines. They love to ask questions about this, and it's really, really easy, but people forget the qualifications, okay? You gotta be continuous, okay? And then two cases where you are continuous but not differentiable, sharp points, and vertical tangent lines, okay? So there's just my explanation of differentiable diffees, the abbreviated version of it. So I've got some problems here to practice. I think it says determine where F is differentiable. Focus on where it's not, okay? Look for sharp points, look for vertical tangent lines, and that's really what I want you to focus on, okay?